Hello, everybody. We are back with another lesson, and after quite a while, because I've been pretty busy, but now I am back and I am ready to get going with this because we are almost finished with this unit, and after this unit, we will officially be finished with everything that I've learned from Intro to Circuit Analysis. And I just wanted to mention, I feel like I haven't said this as much in all my other videos, but I wanted to make a note that all of this is from my point of view in terms for this specific course, and I don't claim to be like super absolutely knowledgeable about this, but as someone who took this course, I think that there are some insights that I wish that I had known if people had told me how to do some things, and it would have made my life a lot easier when I was taking this course. And so hopefully that helps you guys. And of course, all professors are going to be different, all teachers are going to be different, all students are going to be different, but hopefully this is something that will help you guys. So anyway, enough yapping, let's get right into the lesson. So today we are going to be talking about solving circuits in steady state. It's going to be very, very familiar because we're going to be using a lot of nodal analysis, and it's going to be treated kind of like one of our circuits that we've done way back in Unit 1. There are a few things to note, and I know that we've gone through a lot of math prep videos before this, and there's a reason why. And the reason is that we are now going to be thinking about impedance. Now, impedance is represented by a Z, and impedance has a real part and an imaginary part. And the real part is the resistance, the resistors, and the imaginary part is the reactance. Now, the reactance is basically how the capacitors and inductors behave with one another, right? We know from transient analysis that capacitors and inductors can move the energy around, and they can be blockages or they can be closed circuits to allow all the energy to go through. So to quantify it, we attach something called reactance, okay? And to actually quantify for each inductor and capacitor, we can get we can turn it into the frequency domain, right? And say j omega L and 1 over j omega C. Okay, so every single inductor and capacitor can be represented in steady state analysis. And we have this informative graph, which might not make too much sense right now, but essentially this shows the phase, right? Because we have a complex number. We know that we can write a complex number in polar form from the previous math videos. And in the polar form, this has phase, right? It's encoded, right? And so we can determine whether or not a circuit is more inductive or more capacitive based on this nice little graph. Now here's the workflow that I typically follow and what I was taught with. And basically this is a very simplified version of steady state analysis. The first step we're going to do is make sure all sources are driven by the same omega, by the same frequency. This just makes the analysis much easier, and it's beyond the scope of what I was taught and what you're probably going to learn in an intro circuit analysis class. Number 2 is turn all sinusoids into cosines. This is a personal preference. Some people like writing it in sines, but if you write it in cosines, it's a lot better because you stick to one convention. The third thing is to turn everything into frequency domain. So that is to get everything in terms of the omega. And 4, apply an analysis, which you should be absolutely amazing at doing. And 5, turn it back into the time domain. All right, let's go ahead and get to the first question, the first practice problem. Okay, here is the first problem, and it looks pretty simple, and it is pretty simple. Once we get to talking about it, we can actually solve this in a transient analysis. If we had a switch, we could see, how the capacitor, how the inductor, how the voltage changes in that transient portion. But we have this alternating current, so the forcing function is not going to be constant this time. It's going to be a cosine, which is a little more difficult, but that's mostly a differential equations problem and beyond the scope of what I'm going to teach. So remember, this cosine omega t plus phi, any cosine can be written like this. And so here's our nice omega that we're trying to convert everything into the frequency domain. And so let's go ahead and do that. So we're going to look at, if you notice, actually, in step 1 and step 2, we are supposed to make sure all sources are driven by the same omega to simplify all of this circuit very nicely, and to turn all sinusoids into cosines. But the thing is, we only have one, and it's already in cosine, and so we don't need to consider that. So let's go ahead and move on and call step 1 instead, turn everything to frequency. And so basically, the first thing we're going to do is turn the voltage into a frequency domain. And I like to write my voltage as V like this in the frequency domain so that I can determine that this voltage is in the frequency domain, and it looks pretty nice. So we're going to turn this guy into the polar form, which, if you guys remember, it's a e to the j phi. And so we're simply just going to copy this down, 6e to the j, and there is no phase, so it's just 0 degrees. And if we remember from our simplifications, e to the j0 is just 1, and so we get 6. So it's going to be 6. The voltage is going to be 6 in the frequency domain. And now we've got to go ahead and find the impedances of each of the components. And we have one capacitor, one inductor, and one resistor. So I like to call the capacitors ZC. The capacitor is going to be 1 over J, and the omega is 3, and the capacitor has farads of 1/5. And I like to simplify this. I like to move my J's up to the top, and we know that 1 over J is equal to negative J, because if you multiply J over J, you will get negative J. And so I'll put the J on the top, and I'll flip the fraction, and I'll add a negative sign. So that is the impedance of the capacitor. Now the impedance of the inductor is going to be J omega times 14, because that is the henries, and we get J42. And the resistor, I mean, you don't technically need to write it, but it's ZR because the resistor stays the same, right? It doesn't introduce anything. It's just still in, still 10. Now for step 2, we're going to apply a nodal analysis, because we want to find the V of t at this node right here, and it's simply just that. We're going to say at n1 v minus 6, right? Because our v is actually constant in the frequency domain, so it's going to be v minus 6 over 10 plus, and then we have v minus this guy right here, or not that guy, but v minus 0 because it's directly connected to ground, divided by negative 5, 3, J. Okay. And plus V minus 0, and we have our impedance through this inductor right here. That is defined as J42 equals 0. All right, we are going to go ahead and simplify this. So I'm going to multiply by a factor of 210. And the reason why I'm going to do that is so that we can completely get rid of everything in the denominator. And let me go ahead and just reflip this 5 over 3. I'm going to go ahead and multiply by 210. All right, so we're going to go ahead and we're going to get 21v minus 126 plus j 126. And how I got this was I applied the 1 over j here. So it became negative j. The negatives canceled out. And same right here. It would be minus j 5 volts, 5v. And this is technically supposed to be that nice frequency thing. But, you know, it's easier to just write down the v. You just have to remember here that it's back in the frequency domain. Now what we're going to do is actually combine like terms. Okay, so the first thing that we're going to try to do is combine all of the v's together because we want to factor out that v, right? I forgot a v right here. So this is going to be 21v minus 126, or actually let's say plus 126, and this is plus j 121v equals 126, like so. We're going to factor out that v. We're going to get 21 plus j 121 equals 126. V equals 126 over 21 plus j 121. And now here we're going to do something a little bit different, still part of the nodal analysis step, but we're actually going to convert this into the polar form, which we learned in previous videos. And so we know how to convert to polar form. We need an amplitude first, and the magnitude of the amplitude. And so we are going to say 21 squared plus 121 squared rooted, and that is going to be 122.809, okay, to 3 decimal points. And then we're going to need our phi, and our phi is going to be tangent -1, and thankfully we are in the first quadrant for this first one, so it's pretty easy. And to visualize that, we're in the first quadrant, so it's going to be somewhere right here, okay? And we're going to take 121 divided by 21, and that is going to be approximately 80.154 degrees. And so plugging this back in, we're going to get v is equal to 126 over the magnitude, 122.809, e to the j 80.154 degrees. Okay. And because this is in polar form, we can actually apply exponent properties. And so our reduced, so this right here is going to be 80.6, right? 0.154, 154. It's going to be v is equal to 126 over 122.809, and we can move our exponent out of the bottom and just put a negative number right there. Negative 80.158 degrees. So actually, at first we were in the first quadrant. This individual thing was in the first quadrant, but v itself is actually in the fourth quadrant, like so. And so when we simplify this down, we get 1.025 cosine in our original omega 3t minus 80.154 degrees. And that's how we get, this is This, remember, is in the phasor form, and when we are changing back, when all the frequencies are the same, we can just plug in the same frequency. It's the same thing. And this is no longer the frequency V, but VSS of t. And this is the answer. So pretty simple. Let's go ahead and do our last example. Okay, so now we are going to solve this circuit. Now, it looks pretty crazy, and I did make it a little crazy, but the idea is super easy. What's going to trip most people up, what trips me up when I was making it also, is that it's a lot of algebra mistakes, right? And so right now we're trying to find VSS of t right here at this node, okay? So the first thing that we're going to do is actually apply our little algorithm thing, and step one is to turn everything into cosine. Or actually, no, the first step is to check if everything has the same, see? Well, you can't change the problems, but most likely they're not going to change. The problems are going to be right like that, unless your professor makes you do different. Then you would have to use a completely different analysis rather than the steady state analysis that is simplified. But basically, we got to check if all of the frequencies are the same, and in this case they are after this edit right here. And the frequency is 2.5, and so that kind of goes without saying. I'm not going to write it down, but we are also going to turn everything into cosines, because I see that we have a power source that is a sine. So we're going to go ahead and turn this guy into a cosine, and we turn it into a cosine just by simply subtracting 90 degrees from the argument. So plus 8 degrees minus 90 degrees right here, which is going to be negative 82 degrees. And step 2, we're going to convert to frequency. So the first thing that we're going to convert is our V. From here, all we need for the phasor form is the amplitude and the phase. And that is going to be 40e to the j 109 degrees. And then we also have to convert that current, which is going to be, now we're going to use the cosine now, so 2 and negative 82. Now we have a lot of converting to do here. So this is a resistor, so that's good, and this is a resistor, that's good. So we need to convert this inductor and this inductor and this capacitor. So let's go ahead and do those inductors. So we're going to call inductor 1 L1, right? L1. And L1 is going to have the 8 henries right here. So it's going to be J times 2.5 times 8, which is equal to J20. Then we're going to have the second inductor, which is J times 2.5 times 16. Convenient numbers. That's going to be J40. And finally, we're going to solve for the capacitor, and there's only one capacitor, so we're just going to call that ZC. And the capacitor, it's going to be J times 2.5 times 1 over 20, which is equal to 8 over J. Okay. Now, what I would like to do is take this and simplify it down. So the cool thing about turning everything into the frequency domain, especially the capacitors and inductors, is that you can treat them like resistors. So that means that all of these quote-unquote resistors are in parallel with each other. So a little sub-step is we're going to simplify the middle. So everything is in parallel, so we're going to use R1, R2 over R1 plus R2. Except this time we're going to use Z1, Z2 over Z1 plus Z2. And in this case, we are going to be combining the the capacitor and the inductor. So I'm going to say ZC times Z. Actually, no. Let's go ahead and combine the resistor first. And I'm going to call that R2 because we have an R1 right here. So ZC times R2, ZR2, ZC plus ZR2. And that is going to be equal to 8 over J times 40, 8 over J plus 40. And now here is where the math, really comes in, and you have to be very, very careful. So I'm going to go through this, and yeah, so it's going to be negative J, and then 8 times 40 is 320 over, and this is going to be 40 minus J8. And here we're going to multiply by our complex conjugate, so 40 plus J8, 40 plus J8, because we want to remove the J from the bottom. So the top effectively becomes negative J 12,800 plus 2,560 over 1,600 plus 64. And if we simplify this down, we get 20 minus J 100 over 13. Now we've solved for this portion. Now we've got to solve for the entire portion, the green portion. So we're going to take our result from here, and we're going to go ahead and plug it into another another one of these. So it's going to be, instead of ZC, it's going to be ZCR2 in parallel with ZL2. Yes, ZL2 right here. So we're going to go ahead and put that in. 20 minus J100 over 13 times J40 over 20 minus J100 over 13 plus J40. And this, I'm going to go ahead and simplify it, but what I'm going to do is multiply this guy across by multiply the J40 out. We're going to get J800 plus 4,000 over 13. And on the bottom, we've multiplied by 13 over 13 so that we can add them together. We're going to get 20 minus J100 plus J 520 over 13. The 13s cancel out, and we are left with 4,000 plus J800 over 20 plus J420. Now, once again, we're going to take the conjugate, the complex conjugate of this, and we're going to take the complex conjugate of this, the complex conjugate being 20 minus J420 over 20 minus J420. And simplifying that, we get 80,000. Yeah, sorry for the giant numbers, guys, but this is the reality, is that you're going to be working with scary numbers like this, and you're going to feel like you're doing things wrong, but the reality is you're probably doing it right, as long as you adhere to the same concepts over and over and over and over. And on the denominator, we're going to get 400 plus 176,400. And all of that simplifies down if you just put this into a calculator and make sure that you are aware of combining like terms, you're going to get z, and I'm going to call it just z1. So this whole thing in here is going to equal z1 is equal to 2.352 minus j 9.411. And so that's that for the middle simplification. But that's only part of the problem. We have another portion that we can simplify, but thankfully this one is very easy. That one is going to be z2, and z2 is comprised of r1 and L1. So it's just going to be 20 plus J20. So the next step is apply a nodal analysis. Now in the last problem, we did not change into phasor form until the end. In this problem, it actually probably is nicer to go ahead and, like, once you've set up the nodal equation, to go ahead and convert everything into polar. And the reason why I prefer this is because I don't want to write all of this all at the same time, right? And I also like to keep track of the phases. So let's go ahead and make the nodal analysis. So we're going to have V minus this guy in the frequency domain over this guy also in the frequency domain. So that's going to be minus 40e j 109 degrees over 20 plus j20 plus, and then we've got this right here, this configuration going to ground, v minus 0, or just v, over 2.352 minus j 9.411, which is what we've just found right here. And then minus, because we have a current going into the node, 2e to the negative j 82, like so. And now we are going to convert these guys into their polar forms. So I'm not going to go through the math. You should be able to know how to do this already. So you're going to get 28.2843 e to the j 45 degrees. And then this guy right here is going to equal to, I guess, 2.3 minus j 9.4 is going to equal to 9.70143 e to the negative j 35.968 degrees. And these are going to be plugged back in here. Now I'm going to move to the next page and we're going to complete the nodal analysis. Alright, we're almost done, guys. So now we have our equations like this in their phasor form. Oh, I just realized, guys, I made a mistake. This is actually negative 75.963 degrees. So let's go back and change that right here. I was actually gonna write the wrong number. But yeah, this is why I wanted to do this, because I make a lot of mistakes too. So minus 2e to the negative j 82 degrees equals 0. Okay, so now we're going to go ahead and simplify everything. So I'm going to go ahead and move all of the exponents into their respective places. So like into the right places rather than on the bottoms. So this has to be split up down the middle. So this is going to be v over 28.28 e to the negative j 45 degrees minus, and 40 divided by 28.28 is going to be 1.414 e to the j 64 degrees plus v over 9.70 e to the j 75.963 degrees minus 2e to the negative j 82 degrees equals 0. And now, once again, like what we did before, we're going to combine like terms, and we're going to factor out this v and move every constant thing to the other side. And now, we're going to have to combine all of these guys in phasor form, but the problem is we can't really combine them in phasor form. So what we're actually going to do instead is we're going to turn this back into the rectangular version, the complex version, add them up, and then divide it out, okay? So we're going to see that e to the negative j 45 degrees, and using Euler's identity, which is cosine negative 40, like cosine theta, plus j sine theta, is going to equal to root 2 over 2 minus j root 2 over 2. And e to the j 75.963 degrees is simply equal to 0.242 plus j 0.970143. Now remember that these portions are just these portions right here. So we still have to divide by these guys. So hopefully you've saved them in your calculator. But simplifying it down, we get pretty nice numbers. If you maintain all of the precision in your calculator, you should get 0.025 minus j 0.025, which makes sense, plus 0.025 plus j 0.1. And on the other side, once you've plugged in all of these things, like you've done right here using Euler's equation, you're going to get 0.6199 plus j 1.27109 plus 0.278 minus j 1.9805. And you're going to have v is equal to 0.898 minus j 0.70944 over 0.05 plus j 0.035, like so. And then finally, we're going to have our last conversion to phasor form, and we're going to get 1.144 e to the negative j 38.3007 over 0.09013 e to the j 56.3099, and I got that by just turning these two things into phasor, which we've done before, so I won't write that to waste time. And that's equal to 12.6989 e to the negative 94.6106. And then, finally, we can put this into the time domain. VSS of t is equal to 12.6989 cosine 2.5t minus 94.6106 degrees. And this is the answer. So that was a lot of algebra, and I'm sure that there was an easier way to do this. I'm sure that you could figure out an easier way to do this, but this is how I did it and do it, and it's very error prone, definitely for in the algebra case, but hopefully you were able to see all of the steps, drawn out. And yeah, that's it. Super simple. It's just this is what gets a lot of people, is the it's the math. That's why we dedicated a few videos to the math, because it can get confusing. But yeah, that's it.